Hi guys. Today I want to show you a little bit more about electron configurations. There are a couple of things to remember when we are doing electron configurations. First, these give the approximate location of each electron in an atom. So we don't exactly know with 100% certainty where the electrons are, but we have a really good idea when we write the electron configurations. We also want to remember that if we're talking about a neutral atom, the atomic number, which equals the number of protons, will also equal the number of electrons. And that'll be important to help us figure out exactly how many electrons we need to be accounting for. So there are a couple of rules for us to keep in mind, and there are a couple different kinds of orbitals. So we have s orbitals that can hold a maximum of 2 electrons, p orbitals that can hold a maximum of 6 electrons. But for p orbitals, we actually have 3 suborbitals, meaning that there are 3 individual p orbitals that make up the p shell in the atoms. Similarly, d orbitals, which can hold a maximum of 10 electrons, have 5 subshells or 5 suborbitals, making up the complete d shell. And then f orbitals can hold a maximum of 14 electrons within 7 total suborbitals. Now, as for how the electrons get filled, the lowest energy levels are filled first. So on this diagram, which is an orbital notation diagram, you can see that we increase in energy as we move up. So the first orbital that is always filled is the 1s orbital. And you go to the next orbital as you move up the diagram. If there are 2 electrons occupying the same orbital, they're going to have opposite spins and travel in opposite directions. So just like we drive with lanes of traffic moving in opposite directions, electrons are going to spin in opposite directions when they have the same orbital. Now, atoms, if they can, want to put 1 electron into each suborbital first before they go back and pair up electrons in those suborbitals. And that's a spacing issue. Everybody kind of wants to have their own space. So do electrons, if we can allow them to. So let's look at an orbital notation for a specific atom. So let's say we want to know about lithium. So lithium is atomic number 3 on the periodic table. So that means that we have 3 total electrons that we want to account for. That's a little bit better for 3. So since we're going to occupy the lowest level first, our first electrons are going to go in the 1s orbital. So my first electron goes into the 1s orbital, and I represent that by an arrow kind of pointing up. There's my first electron. Now I need to fill up this orbital before I can move on, so the second electron is also going to go in the 1s orbital. And I can show that they're spinning in opposite directions by making this arrow point down. Now, this orbital is now full because it's an s orbital and it can only hold 2 total electrons. So that means my third and final electron in my lithium atom goes into the next energy level and the next orbital, and that's 2s because that's the one directly above where I started. And now I can see that I have all 3 of the electrons that should be in lithium represented here. the first two in the 1s orbital, and the third one in the 2s orbital. So if I was going to write out my configuration, I would say that we have in the 1s orbital 2 electrons, and I represent the number of electrons as a superscript on the orbital letter. And my last electron is in the 2s orbital, so I would say 2s1. So this would be the electron configuration of lithium. 1s2, 2s1. Let's do another one. Let's say that I wanted to do potassium. So potassium is element number 19. And that means that we have 19 total electrons in a neutral potassium atom. So I need to account for all 19 of them. So we start at the lowest level, and we're going to work our way up, filling in each orbital. So my first two are going to go in the 1s orbital. Moving up my diagram, that brings me to 2s. So my next two will go into the 2s orbital. Moving up the diagram, the next energy level is 2p. And this is where that rule about filling in and sending them spinning in the same direction ties in. Because instead of putting the next two right together like this, instead, what happens is that it fills like this. There's 3 electrons, and they're spinning in the same direction, all with up arrows. But I spaced them out. I gave them their space because I had that option. But now I'm left without any other options because I have to fill the 2p orbital before I move on. And p orbitals can hold a maximum of 6 electrons. And I only have 3 drawn here. So electron number 4 in this orbital is going to be here, and then 5, and then 6. So if I look at my total number of electrons right now, I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we got to get to 19. So 9 more to go. If I go to my diagram, I can see that the next orbital I come to is 3s. So I can put 2 more into 3s. So there's 12. Next comes 3p, 13, 14, 15, 16, 17, 18. So now the 3p orbital is full, but I have 1 more electron, and it's going to go into the 4s orbital. So now I can count, and I have 19 electrons accounted for. So now I can write my electron configuration. So it starts with 1s, and there are 2 electrons in the 1s orbital. And then we filled the 2s orbital, so 2s, 2. Then we filled the 2p orbital, and we put 6 total electrons there. So we're going to write 2p, 6. Then we filled the 3s orbital with 2 more electrons, so 3s2. Next came the 3p orbital that we put 6 electrons in, so 3p6. 6. And last but not least, we didn't fill, but we put one final electron in the 4s orbital, 4s1. And that is the electron configuration for potassium. Now, if you don't have the orbital notation handy, which most of the time we don't, there is a nice way that we can use the periodic table itself to help us write configurations. Because the periodic table can be broken down into electron configuration blocks, where we can see here in blue, this is known as S block. Here in orange, this is known as D block. The pink is known as F block, and the green is known as P block. Now, there are 7 maximum energy levels, and there are 7 maximum rows that we have on the periodic table. So each row, which is also called a period, corresponds to the energy level that the elements in that period or row exist in. The columns or groups within each block correspond to the maximum amount of electrons that you can put into that orbital. So there are 2 columns or groups in S block because S orbitals can hold a maximum of 2. There are 10 columns or groups in D block because a D orbital can hold a maximum of 10 electrons. There are 6 columns or groups in P block because a p orbital can hold a maximum of 6 electrons. And there are 14 columns or groups in F block because an F orbital can hold a maximum of 14 electrons. So notice that helium, even though it's over here with the rest of P block, is colored blue. And that is because helium is actually part of S block because it only has 2 electrons. Its atomic number is 2, and they exist in the first energy level within the S orbital. So that is why helium is part of S block. Now, when I want to use the periodic table to help me write configurations, I treat it like a book, meaning that I read through the table from left to right, row by row, until I reach the element that I am trying to write the configuration for. So for example, let's say that I want to write the configuration for magnesium. So magnesium is here and it's element number 12, which means we want to account for all 12 of the electrons in the magnesium atom. So we always start in the first row in S block. So we start with hydrogen and we're going to go row by row, reading across the table and write our configuration. For every element that we pass through, we add another electron. So for example, if I'm reading across row 1, then I'm going to be completing the 1s orbital. So I would write 1s2. Because in the first row, I moved through 2 total elements. So I've accounted for the first 2 electrons. Now that I've completed that row, I move on to the next row, which is row 2. So now I write 2, representing row 2, or period 2, and I keep going. I move through the S block of row 2, so I completely fill up the S orbital here. So I would write 2s2. And we keep moving straight across row 2, but now I hit a new block. My color changed. So I need to say that we are now in a p orbital, and we're filling up p orbitals because we hit p block. But we're still in row 2. So the 2 doesn't change, but the kind of orbital does. So we have 2p now, and we're moving all the way through row 2. So we're going to be filling up the p orbital and putting 6 more electrons into our atom as we move through the 6 other elements here on row 2. Then I come to the third row, so I write 3, and I'm back in the s block, so I'm in an s orbital again, and I'm moving through 2 more elements, so I'm going to put 2 electrons into that last s orbital, and that brings me to magnesium. So I'm going to stop because I'm where I'm supposed to be now. Now what I can do is, if I want to double check myself, since I know that there should be a total of 12 electrons in my magnesium atom, if I add up the exponents or the superscripts on each of my orbitals, if I've done this correctly, they should add up to 12. So 2 plus 2 gives me 4, plus 6 gives me 10, plus the final 2 does give me 12 electrons that we've accounted for here. So chances are that this is the correct electron configuration of magnesium. Let's look at another one. Let's say that I want to look at iron. So if I'm going to look at iron, iron is atomic number 26. So I'm going to have 26 total electrons in my final electron configuration. But we always start in row 1 at the top. So I'm going to go completely through row 1, which means the first part of my electron configuration is going to be 1s2, because I go through 2 total elements in the row 1. Now that I've completed that row, I move on to row 2. So now I'm in row 2. I'm going to go through the s block of row 2. So I'm going to put 2 more electrons into that s orbital. I'm going to go straight across to the p block, and I'm going all the way to the end of row 2, which means I'm going to fill up 2p6. Remember, every time you get to a new block, you need to write your row number again and then state the letter that associates with the orbital you're in. Now that I've filled up 2p and I've come to the end of period 2, I'm going to go to the beginning of period 3. And I'm back in S block, and I'm going to go all the way through S block, so 3s2. Coming straight across, we're in a new block, but I'm still in row 3, so 3p. We're going to go all the way to the end of period 3, so it will be 3p6. Now we're going to start the beginning of period 4, so 4, and this is S block again. We're going to go through S block, so 4s2, And now something strange happens because we would think maybe that this would be 4D because we are now in D block. But if you look right here, it says that this is 3D. Now, why is that? How come, even though that we're on period 4, this is known as 3D? Well, the reason is D orbitals are higher energy than S orbitals. So in the third energy level, the D orbitals sort of spill over into the fourth energy level. So they kind of overlap those 4s orbitals. So think of them kind of like an older sibling who puts their legs over your lap or leans into your space in the car just because they're so much bigger and they want to take up more space. You can sort of think of it like that. But as long as you can remember that with the d orbitals, and even down here with the f orbitals, you can see that this is called 4f and this is called 5f. They just kind of spill over into each other. So instead of saying 4D, which would be incorrect, we're going to follow what it says and we're going to say that this is 3D. And we're only moving through 1, 2, 3, 4, 5, 6 elements to get to iron. So we're going to write 3D6. So then this should be the electron configuration for iron. And if we add up our exponents, 2 and 2 and 6 give me 10, plus 2 more is 12, plus 6 more is 18, plus 2 more is 20, plus the final 6 gives me 26. So it does seem like we did it okay. Let's look at one more, and I'll make it a D block element so we can practice that again. Let's say that we want to write for zinc, the electron configuration of zinc. So it's atomic number 30, which means we have 30 total electrons in order to work our way to zinc. So just like always, we're going to start at the top in row 1, and we're going to go all the way through row 1. So we start 1s2. That brings us to row 2. So we have 2s, 1, 2. Coming across to 2p, 1, 2, 3, 4, 5, 6. Now we're in 3s, 1, 2. Straight across to 3p, all the way to the end is 3p6. Then we come to row 4, so 4s, 2, 1, 2. And just like last time, it's not 4D, it's 3D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D, 10. 2 and 2 and 6 is 10. 2 and 6 brings us up to 18. 2 and 10 brings us up to 30. So that should be the electron configuration of zinc. Hopefully that helped you out a little bit, but if you do have more questions, please reach out to me.